This is our final report for Intelligent Recommendation and Indexing System for Deep Learning Papers. Deep learning research has grown exponentially, creating challenges in navigating the vast volume of interdisciplinary literature. Our project addresses this by simplifying exploration and offering personalized recommendations tailored to user preferences. The challenges include overwhelming research volume, cross-field complexity, and the lack of personalized tools. Existing solutions often fail to contextualize research effectively. Our platform integrates a domain-specific knowledge graph, semantic embeddings, and retrieval-augmented generation. This enables efficient document retrieval, summarization, and question answering, offering a unified and scalable solutions for researchers. Our data is sourced from Archive, Papers with Code, and Semantic Scholar. Archive provides titles, abstracts, and publication dates, while Papers with Code contributes metadata on tasks and methods. Semantic Scholar enriches the dataset with citation relationships and bibliometric details. The dataset includes over 30,000 papers, over 10,000 citation relationships, and covers over 100 research tasks and methods. Semantic embeddings further enhance contextual understanding. Key challenges include inconsistent data quality, integration of heterogeneous sources, and API rate limits requiring optimized retrieval. In our project, preprocessing was essential for ensuring data consistency and usability. Cleaning involved tokenizing and resolving inconsistencies in titles and abstracts, while duplicates were handled using identifier matching. Key challenges include API request limitations, addressed through asynchronous API requests, and integrating heterogeneous data, which was solved by aligning both structured and unstructured data into a unified knowledge graph. Our project integrates advanced technologies to provide personalized learning experiences. Neo4j efficiently stores and queries the knowledge graph. MySQL manages structured user data, and Weaveates enables fast vector-based retrieval. Semantic embedding generation encodes textual and graph data, while vector retrieval and RAG enhance search and generated responses. Spring Boot, Angular, and AWS ensure scalability and seamless user interaction. Our system consists of four main components. Knowledge Graph Storage combines Neo4j for graph data and MySQL for user information. Back-end services use Spring Boot for robust integration, while the front-end interface, built with Angular and D3.js, offers interactive visualizations. Cloud deployment is handled via AWS with Docker for scalability. Data flows from Archive, Papers with Code, and Semantic Scholar is processed into Neo4j's graph and drives user recommendations based on analytics. And this is a demo of our project. The main page of our project features a daily renewed subgraph fetched from our knowledge graph. Each node is a paper, and a link is a citing relation. Different colors of nodes indicate different tasks they apply to. The size of the paper node depends on the number of papers that cite this paper. We can zoom on the graph and directly navigate to the clicked paper. And this is the detail page of a paper. It demonstrates the abstract of the paper, the authors of the paper, the task this paper is applicable to, and the method this paper uses to solve the problem. We also provide GitHub code links sorted by the stars. Moreover, if you are logged in, you can gain access to the Graph RAG-based paper summarization. Different from traditional prompt-based method, Graph RAG provides more in-depth insights and analysis based on our knowledge graph. As you can see, the core idea is extracted from the abstract, and methods and tasks are extracted from relations in the knowledge graph. This is a demonstration of the vectorized search function, which takes semantic information into account. As we type GPT-3 in the search bar, the results returns strongly relevant papers regarding to GPT-3. As you can see, the second result is the original paper proposing GPT-3. By clicking on the results, we can navigate to the detail page of the paper, and this is another demonstration of GraphRAG. We borrow the prompt from GraphRAG as a sample question to further show the ability of RAG in searching and open-ended question answering. By asking, what is few-shot learning? GraphRAG searches few-shot learning extensively in a knowledge graph, and sort and truncates the results by relevance. Based on these results, LLM generates a context-aware answer and describes it with easily readable human language. If you have logged in, we'll try to record your trace and favorite papers. In this case, I have steered some papers that are monumental in the field of computer vision. Back to the top, these paper tabs in pink are GAT recommendations. Instead of just recommending papers with most citation, GAT recommendations tend to prompt users to explore some interesting areas which are still strongly related to user favorites. Here, we can see papers solving tasks like age detection, semantic segmentation, object detection, and we can also expect some leading papers like ImageNet and YOLO v3. In this experiment, we evaluated the recommendation system and graph attention network for predicting user paper interactions. The training loss curve shows steady convergence, indicating effective optimization over 100 epochs. The ROC curve demonstrates strong performance with an AUC of 0.91, validating the model's robustness and predictive accuracy. While results are promising, further improvements are needed in computational efficiency for subgraph queries and vector retrieval. This table presents the recommendation accuracy and performance metrics of various algorithms combined with their respective datasets. Our approach, GAT and DLKG, achieved the highest accuracy at 0.856, an AUC of 0.91, a recall of 0.79, and an MAP for 0.746. These results demonstrate the superiority of our method in leveraging graph-based data for personalized recommendations. This slide outlines the challenges addressed and future directions of our project. Key accomplishments include building a robust knowledge graph and implementing personalized recommendations. Despite these, the dataset's focus on well-cited paper limits its diversity, and our user behavior model simplifies real-world interactions. Future work involves integrating user-generated content and feedback, enhancing dataset variety, and aligning recommendations more closely with actual user behaviors. And thank you for your watching. We really appreciate your time here.